Hey everyone, and welcome. We're all surrounded by these things. The power bricks for our laptops, the little wall chargers for our phones. They're so common we don't even think about them. But inside these plain old plastic boxes is a world of seriously clever engineering, and it's all designed to do one thing above everything else: keep you safe. So today, we're going to pull back that curtain and take a deep dive into the hidden world of isolated DC power supplies. So let me kick things off with a question for you. What's the single most important and probably most overlooked part of that charger that powers your daily life? The magic here isn't just about turning AC from the wall into DC for your battery. Nope. It's about creating an invisible wall, this protective barrier between the dangerous high voltage from the outlet and the very delicate electronics in your hand, and, of course, you. The answer to that question? Well, it leads us right to the core idea of this whole explainer. Okay, let's really get into this. Over on the left, you've got a non-isolated circuit. Just think of it as a direct, unbroken wire running from the wall outlet straight to your device. Yeah, it's simple, but it carries a real risk of electric shock, and it lets all sorts of electrical noise mess with your power. Now, look to the right. This is an isolated circuit, and the hero of this whole story is the transformer. See that? It creates a physical magnetic gap. There is absolutely no direct electrical connection between the input and the output. Power gets transferred kind of magically, magnetically, right across that gap. This whole principle is called electrical isolation, and it's absolutely fundamental for two huge reasons. First, and most important, is user safety. And second, it creates clean, stable power for our very sensitive electronics. Right, so to really wrap our heads around all this, we've laid out a roadmap with 6 key sections. We just covered section 1, the basic need for isolation. Next up, in section 2, we'll get to know the workhorse of all those little chargers, the flyback converter. Then in section 3, we'll step it up to the forward converter family. Section 4 is where we get into the big leagues with high-power topologies. After that, in section 5, we're going to uncover the brains behind the whole operation, the control systems. And finally, in section 6, we'll zoom out and look at the bigger picture of how these things are designed in the real world. So let's get into it. So our first stop is section 2, the flyback converter. I mean, if you've ever held one of those small chargers for your phone or a modem or pretty much any similar low-power gadget, you are almost certainly holding a flyback. It is the undisputed hero for anything under about 150 watts, all thanks to its brilliant simplicity and low cost. Now, if you're looking at this circuit and thinking, hey, that kind of looks familiar, you're absolutely right. At its heart, the flyback is a really clever twist on a design you might already know. It's basically a buck-boost converter, but with one massive change. That single inductor is split in two and replaced with a transformer. But, and this is the key, this isn't your normal, everyday transformer that just passes energy through. A flyback transformer is specifically designed to store energy in its magnetic field, so it acts a lot more like an inductor. This one unique feature is the absolute key to how it works. The way it operates is this beautiful two-step dance. Think of the transformer core as an energy bucket. So in step 1, when that switch is on, current flows in and starts to fill the bucket, storing energy up in the transformer's magnetic field. Now, what's really important is that during this phase, the output side is completely disconnected. Then, in step 2, the switch flicks off. The magnetic field collapses, that creates a voltage in the other coil, and all that stored energy flies back or gets dumped to the output to power your device. It's just this constant cycle of fill and dump, happening tens or even hundreds of thousands of times every single second. So, what are the trade-offs here? Well, the pros are huge. It has a very low component count, which makes it incredibly simple and cheap to build. Plus, you can easily get multiple output voltages just by adding more windings to that transformer. But here's the catch. That constant fill and dump action creates really high peak currents and high voltage stress on the components. That's why it's pretty much limited to lower power. You almost never see it above 150 watts. And here's something really important to remember. In those ultra-cheap, poorly made chargers, if that isolation barrier fails for any reason, the flyback's design could potentially expose you to lethal voltages. It's a pretty powerful reminder of why good engineering really, really matters. So that brings up a good question. The flyback is great for low power, but what if we need more? What if we need better efficiency and a little less stress on our components? Well, that's where the forward converter family comes into play. Let's move on to section 3 and check out this more direct approach. Okay, right off the bat, the forward converter definitely looks a bit more complicated, and that's because its operation is fundamentally different. Unlike the flyback, which stores and then transfers energy, the forward converter acts more like a true transformer. When its switch is on, energy is transferred directly across that magnetic gap to the output. You can almost think of it as an isolated version of the very common buck converter. But this direct energy transfer creates a really unique and critical engineering problem that designers have to solve. And that problem is what we call the reset problem. See, because we're using a real-world transformer, not all the magnetic energy gets perfectly coupled from the primary side to the secondary side. Some of it, we call it magnetizing current, builds up in the transformer's core while the switch is on. If we don't do anything about it, this energy just keeps accumulating cycle after cycle until it completely saturates the core. That basically turns it into a short circuit and poof, it destroys the switch. So the big puzzle for engineers is, how do we get rid of that leftover energy? Well, engineers came up with two really brilliant solutions for this reset problem. The classic way, on the left, is to add a third or tertiary winding to the transformer. When the main switch turns off, this extra winding gives that stored magnetic energy a path to flow safely back to the input source, which resets the core for the next cycle. Pretty clever. A more modern and robust solution, on the right, is the two-switch forward converter. This uses a second switch and a couple of diodes that act like a safety valve. When the switches turn off, the diodes clamp the voltage, preventing dangerous spikes, and safely returning that magnetizing energy to the source. This design is fantastic for higher voltage applications because it so elegantly limits the stress on those expensive switches. Okay, now we're stepping into the big leagues. For applications that need hundreds or even thousands of watts, we're talking about beefy server power supplies, industrial gear, even electric vehicle chargers. We need designs or topologies that are even more efficient and powerful. So welcome to Section 4, where we meet the heavy-duty workhorses of the power electronics world. This table does a great job of showing the progression of these high-power designs. Let's just walk through it. The push-pull converter uses a special center-tapped transformer, which lets it drive the magnetic flux in both directions, positive and negative. This gives it excellent use of the magnetic core. The half-bridge and full-bridge topologies do something similar, but without needing that special transformer. Now, look closely at that row for voltage stress. This is the key insight here. Notice how the push-pull switch sees double the input voltage? That is really tough on components. But look at the bridge topologies. They are much, much kinder to our switches, clamping that stress to just the input voltage. That is a massive advantage when you're dealing with high power. And that brings us to the king of high power, the full bridge converter. By using 4 switches, it can apply the full input voltage across the transformer's primary winding in both directions, positive and negative. This just maximizes power transfer and core utilization, making it the absolute workhorse for the most demanding applications you can think of. And a really cool feature of all these transformer-based designs is that you can get multiple isolated outputs from a single core. Just think of a standard PC power supply. It generates the plus 12V, plus 5V, and plus 3.3V that your computer needs, all from one central transformer. So far, we've really only talked about the muscle, right? The hardware topologies that switch and move all this power around. But none of it works without the brains. And that's the sophisticated control system that makes sure you have a stable, regulated output voltage no matter what the load is doing. For Section 5, things get a little more mathematical, but the core idea is absolutely fascinating. You see, the fundamental problem for a control engineer is that a switching power supply is this chaotic, constantly changing system. Its entire circuit structure is different depending on whether the switch is on or off, and this is happening thousands of times a second. You just can't analyze it with standard linear circuit techniques. So engineers use this powerful mathematical trick called state-space averaging. This technique brilliantly takes the two different states of the circuit, the on state and the off state, and it mathematically blends them into a single, averaged, linear model that we can actually analyze. And as this quote really highlights, the key to the whole thing is using the duty cycle, which is just the fraction of time the switch is on, as the weighting factor. By doing that, we create one simplified linear model that behaves, on average, just like the wildly chaotic switching circuit. This process of linearization is the absolute key that unlocks our ability to design a stable feedback loop. It turns a wildly nonlinear system into something predictable and, most importantly, controllable. So, what does a well-designed control system actually get you in the real world? Well, first, a rock-solid, stable output voltage that doesn't drift all over the place. Second, a lightning-fast response when the load suddenly changes, like when your computer's CPU goes from idle to full power in a microsecond. And, most importantly, it prevents the entire system from oscillating or becoming unstable. Engineers do this by carefully designing compensator circuits, often called Type 2 or Type 3 compensators, to make sure the feedback loop has a healthy phase margin, which is just a key technical measurement of its stability. All right, we've covered the heart of the power supply, the isolated converter and its control system. But in a real-world product, there are other essential pieces that make up the whole puzzle. So for our final section, let's just briefly zoom out and look at the full picture of a practical system design. One of the most critical parts of any modern power supply is the power factor correction, or PFC stage. See, when you rectify AC power from the wall, the circuit naturally draws current in these sharp, ugly spikes. This is terribly inefficient, and it puts a ton of harmonic stress on the entire power grid. So to fix this, we put another converter, usually a boost converter, right at the front end. Its only job is to actively shape the input current it draws, forcing it to follow that nice, smooth sine wave of the input voltage. This dramatically improves power quality, and it's actually required by regulations all over the world. But that's not all. A practical design also needs things like robust EMI filtering to stop switching noise from escaping, and a thermal management system with heat sinks and fans to keep all those hard-working parts from overheating. Wow, we have covered a huge amount of ground today, from basic magnetics all the way to some pretty complex control theory. So let's just take a second and boil it all down. If you take away just 3 things from this explainer, make it these. Number 1, isolation using a transformer is fundamentally all about your safety. Number 2, the choice of topology is a direct function of the power level you need. It scales up from the simple flyback to the forward family and all the way up to the powerful bridge converters. And number 3, none of this works reliably without a precisely designed feedback control loop to guarantee stability. And that brings our journey for today to a close. But of course, the learning never has to stop here. And we really want to know what you're curious about. Where should we go next? Would you be more interested in a really deep dive into the nitty-gritty math and circuit design of a Type 3 compensator? Or would you prefer a more hands-on, practical guide to actually building and simulating a flyback converter in a program like PySpice? Honestly, the choice is completely up to you. Both of those are advanced, absolutely fascinating topics, and your feedback directly shapes the content we create here. So please let us know which path you'd rather take by leaving a comment down below. We genuinely read every single one of them. If you want to keep building your expertise in these complex but really critical topics, make sure you subscribe to the channel for more deep dives just like this one. If you learned something valuable today, hitting that like button is a huge help for us. And of course, if you have any questions at all or other topic suggestions for the future, the comment section is the best place to share them. Thanks so much for hanging out with me today, and we'll see you in the next one.